Assalamualaikum and hi everyone. We from Group 4, we present about solar energy conversion or known as photoelectrochemical cells. This is table of content of what we are present in this presentation. First of all, introduction to solar energy conversion. So what is solar energy conversion? Solar energy conversion refers to the process of transforming sunlight into usable form of energy. This can be in the form of electricity, which is generated through photovoltaic cells or solar panels, and chemical fuel produced via processes like photoelectrochemical, PEC, water splitting to generate hydrogen fuel. So why is it important? First is renewable and abundant energy source. Sunlight is freely available and virtually limitless, making it reliable alternative to finite fossil fuel. Second, reduces dependence on fossil fuel. By harnessing solar energy, we can reduce our reliance on coal, oil and natural gas, leading to increased energy security. Lastly, minimize environmental impact. Solar energy production produce minimal greenhouse gases compared to fossil fuel combustion, helping combat climate change and reduce air pollution. Now, move to understanding photoelectrochemical cells or known as PECs. For the definition, PECs are devices that use sunlight to initiate and sustain chemical reaction, commonly employed for water splitting to produce hydrogen. There are three key components that are important in photoelectrochemical cell. The first one is photoelectrode that absorb lights and generate electron hole pairs. The second one is electrolytes that function to conduct ion to facilitate the chemical reaction. The third one is counter-electrode that completes the electrical circuit and assists in catalyzing reaction. For the further explanation, we will see in the next slide.
So what is the mechanism? The mechanism starts with sunlight striking a semiconductor material called the photoelectrode. The energy from sunlight excites electrons in the materials, creating electron hole pairs. These charges are separated. Electrons travel towards the cathode, while the hole moves towards the anode. At the cathode, the electron participate in a reduction reaction, splitting water molecule to produce hydrogen gas, a valuable fuel source. Simultaneously, at the anode, the hole drive an oxidation reaction, releasing oxygen gas. This entire process efficiently converts sunlight into storable chemical energy, which can later be used as hydrogen fuel or further converted into electricity for practical application.
I will continue for the material of PECs. PEC cells use light energy to decompose water into hydrogen and oxygen within a two-electrode cell. There are three arrangements of photoelectrodes in the assembly of PECs exist, which is one is photoanode made of a N-type semiconductor and a metal cathode. Second, photoanode made of a N-type semiconductor and a photocathode made of a P-type semiconductor. Lastly is photocathode made of a P-type semiconductor and a metal anode. So the common materials for the PECs is tin oxides because due to the most prominent catalyst for efficiency reasons, it also has high stability, non-toxicity and abundant, low efficiency, also absorb only UV radiation. Second is gallium nitride, which is GaN, have a narrow band gap, large enough to allow water splitting to occur at the surface and high stability. Third is silicon, which is semiconductor with excellent electrical conductivity and light absorption properties. Silicon used in both photoanodes and photocathodes. The catalyst for the PECs is which is a platinum used as co-catalyst for hydrogen and has high catalytic activity. As for the electrolyte materials for the PECs is aqueous electrolyte, which is acidic, which is H2SO4 or HCl, which is typical use for the photoelectrodes that operate in acidic condition. Also the alkaline, which is KOH or NaOH, used for photoelectrodes and that operate in alkaline conditions.
Today, I will highlighting the key advantages of photoelectrochemical or PEC technology. First, PEC technology supports clean energy production. It minimizes resource consumption by using sunlight directly, reducing the need for extensive manufacturing or rare materials. It also eliminates the demand for external electricity, making it independent of fossil fuel-generated power. Moreover, it reduces the carbon footprint by converting solar energy directly into chemical energy like hydrogen. Second, PEC technology leverages abundant raw materials. It uses inexpensive materials like titanium dioxide and iron oxide, which are widely available in Earth crust. Additionally, it avoids reliance on rare and costly material using low-cost catalysts like nickel or cobalt. Many of its components are recyclable, which further enhances its environmental sustainability. Finally, PEC technology has a high potential for hydrogen fuel generation. It offers high theoretical efficiency with solar to hydrogen conversion rates exceeding 40%, surpassing traditional methods. Its scalability makes it suitable for both centralized and decentralized hydrogen production, catering to various applications. PEC system can integrate with renewable energy sources like solar and wind, promoting a green hydrogen economy. In summary, PEC technology is a promising solution for sustainable energy due to its efficiency, affordability, and environmental benefits.
Alright, now I'm going to talk about the challenges and limitations of PEC technology. Firstly, the efficiency issues. It caused by the limited light absorption and charge recombination losses. For limited light absorption, some materials used in photoelectrodes have a specific absorption wavelength that determines how much sunlight they can capture. However, the charge combination losses the electrons and holes recombine before they can be used in the reaction, which will waste the energy that could have been used for hydrogen production. Next, the durability. Sometimes the photoelectrodes could be corroded. It may reduce the ability of photoelectrodes to efficiently produce energy, and it makes the overall system less reliable and efficient over time. However, this kind of problems may be prevented by developing more stable materials and improving the protective layers. Lastly, the manufacturing of photoelectrode or PEC technology require a high cost. Precious metals like platinum and iridium are often used as catalysts in PEC system because they are highly efficient and facilitating the water splitting reaction. Treating the photoelectrodes and catalysts require highly controlled conditions to ensure that the material have the right properties. However, advances in material science, manufacturing techniques, and process optimization will be the key reducing costs and unlocking the full potential of PEC technology in the future.
The first current research is about photoelectrochemical system for solar to fuel production. It converts solar energy directly into chemical fuels, primarily hydrogen, through the process of water splitting. It utilizes semiconductor material to directly convert sunlight into storeable chemical fuels. It also uses high efficiency materials such as high purity semiconductor that allow simultaneous solar energy generation and hydrogen production, and also cost-effective thin films that can achieve efficiencies up to 20%. So these systems are designed to reduce complexity and maintenance costs, and more accessible for commercial application. So the application of PEC for solar to fuel production is they can be a energy storage solution and also fuel cells to generate power. So the second one is solar thermochemical hydrogen production. It is a process that utilizes concentrated solar energy to drive chemical reactions, splitting water to become hydrogen and oxygen. For the development of stable and efficient materials, we use nanostructured semiconductor materials because it has high purity semiconductor materials with ultra gentle coating methods to enhance reactor activity. It also allows efficient absorption of solar energy and improve hydrogen production rates. And also high temperature reactor. The development of reactor that can operate at temperature between 500 and 2000 degrees Celsius, it can utilize concentrated solar power or waste heat from nuclear reaction to drive thermochemical cycles. The last one is direct solar water splitting technologies. It is a renewable energy combined concentrated solar power with innovative chemical process to produce clean hydrogen fuel efficiency. So for the development of stable efficient materials, we also use high purity semiconductor that are coated using ultra gentle methods to increase hydrogen production rates, and photocatalysts to absorb visible light effectively and enabling the direct dissociation of water molecules. And the last one is UV radiation utilization. For water splitting, it utilizes photocatalysts that enable efficient photon absorption and redox reaction to generate hydrogen. The application is we can produce sustainable hydrogen production because it provides a clean method for producing hydrogen fuel without greenhouse gas emission, and decarbonization of industrial process such as ammonia synthesis also and refining process, aiding in the decarbonization of this sector. We use the system in industrial applications such as ammonia synthesis, and also for decarbonization of transportation such as long distance trucks, ships and planes, which significantly to efforts aimed at decarbonizing these industries. Future prospect, we aim to increase the efficiency, such as MIT train-like reactor system. We aim to harness up to 40% of the sun's heat. It will improve the efficiency in existing system. This enhancement could reduce costs and make solar thermochemical hydrogen production more competitive. Second one is commercial feasibility. As efficiencies improve and costs decrease, solar-to-fuel production technologies may become alternative to traditional fossil fuel and supporting a transition to a sustainable energy economy. The last one is integration with energy grid, such as direct solar water splitting technology can be integrated into renewable energy grids, providing a reliable source of hydrogen that enhances overall system stability and resilience. Thank you.
In conclusion, PEC represents a groundbreaking technology for producing clean and sustainable energy. By utilizing abundant resources like sunlight and water, PEC directly converts solar energy into chemical fuels such as hydrogen, offering an eco-friendly solution to meet the global demand for renewable energy. While challenges such as efficiency, stability, and scalability remain, ongoing research and advancements in material science hold the potential to address these issues. Importantly, PEC cells pave the way for a greener future, contributing to carbon emission reductions and enabling the production of clean hydrogen fuel. That's all from our group. Thank you.
That's all from our group. Thank you for listening us.